Hello everyone, welcome to Lab 8. In this lab, we are going to discuss numerical differentiation and integration methods. This is very useful when we do not know the analytical functions and we have only data sets. There are three numerical differentiation methods: forward finite difference, backward finite difference, and centered finite difference. As you can see from the picture, there are n number of data points on the line along x direction. It starts from I equals to 0, where the data points are all equally distant, which is represented by h. So for forward difference scheme, if we want to determine the derivative at a certain point, let's say point I, we need to know the value of the function at I as well as 1 point forward, I plus 1. Then we divide the difference of the function values by the difference of those points, or this is called the step size, to evaluate the derivative. Next, for backward finite difference, to evaluate the derivative at point I, we are required to know the value of the function at point I and one step back, that is I minus 1. Then in a similar way as forward scheme, we can get the derivative. But for the center difference scheme, as the name implies, we need to know the function values at both one step forwards and backward data points, and then divide the difference twice the step size. We can determine different orders of derivatives. In the previous slide, we discussed basically first order derivatives with three respective approaches. So for first order derivative, we need actually 2 data points. For second order derivative, we require 3 data points. For example, if we want to evaluate the derivative at data point xi, for forward difference scheme, for second derivative, we need to know 2 points ahead of this xi. Similarly, for backward scheme, we require 2 consecutive points behind this xi. And for a center difference, we see that this xi point, where we want to evaluate the second order derivative, lies in between I plus 1 and I minus 1. Now, regarding the accuracy of each method, we see that with the increase of number of data points, we could improve the accuracy of our estimation. We can precisely determine the accuracy from the Taylor series, where we can truncate the series and look for the order of the step size of the next term, which eventually determines the order of accuracy. But for this lab, lower order method is sufficient and help us learn better. Let's do an example in MATLAB how we can represent the derivatives. Here we have 12 equally spaced data points along with the function values at those points. We are asked here to determine first and second order derivatives at each point, and the scheme must be second order accurate. If we consider evaluating first derivative at the first point, we require 3 points to maintain second order accuracy. In MATLAB, we can write the formula easily, but make sure how you are defining the variables. Here, dy denotes first derivative, and it doesn't matter how you define it, but be careful that the bracket after the parameter means that MATLAB is storing the value in a table where the number designates its position. And on the right side, we simply write the formula according to the finite difference scheme, where brackets for x and y denote that the position of the data point and function values respectively. For example, xi represents the data points -1, x2 represents the data point -0.5, y1 represents function values -3.632 at data point -1, y2 shows the function magnitude at data points -0.5. For the second derivative at the first data point, we require 4 data points to ensure that the scheme is second order accurate. Now, to estimate the first order derivative at the last point having second order accurate, we cannot use the forward method, since there is no data points ahead of this point. So we use the backward difference scheme considering 3 points, so that the order of accuracy is 2 for the first derivative. The same goes for the second derivative, where to maintain second order accuracy we need 4 points in the backward direction. As you can see, in refers here the length of the data points, which is 12 for our example, and is the last point. To calculate the derivatives at all other points in between the first and last points, we can create a simple for loop in MATLAB to represent the derivatives as well as respective data points and function values. For example, we should begin the loop from second data point that will end at the second last data point, which is n-1. You can see that for these points we do not need forward or backward method to ensure second order accuracy. Instead, we use 2-point center method for the first derivative and 3-point center method for the second derivative. After we are done with evaluating first and second derivatives at those 12 data points that have second order accuracy, we can plot them sequentially in MATLAB by using the subplot command. Here, first plot shows the function with respect to the data points. The second plot is for the first derivative, and the third one is for second derivative at the corresponding data points. Since there are 3 plots altogether, by the brackets of this plot command, we mention the position of the plot. For example, 3 refers the total number of plots, then 1 refers the figure number, which is 1, and the next one actually the plot itself. Integration is simply the opposite of the concept of differentiation. For numerical integration in this lab, we are going to briefly discuss Newton-Cotes method, from which we can derive subsequent four formulas such as midpoint, trapezoidal, Simpson's 1/3, and 3/8 rules. Here, let's assume that we are integrating a function f of x in the interval a to b, where the function is considered as a nth order polynomial. And according to the power of this polynomial function, we end up with different integration methods. For example, when the power n is 0, we only have the first term of the polynomial that actually represents us the midpoint rule. When the power is 1, we have trapezoidal rule with the first two terms from the polynomial equation. When n is 2, we have Simpson's 1/3 rule, and for n equals to 3, we get Simpson's 3/8 rule. In your assignment for problem 2, there is a term mentioned, error function. So what does it mean actually? Error function comes from the integral of standard normal distribution, which gives you an idea of the probability that a parameter of interest lies within a range. In MATLAB, the function ERF determines that. For example, if we like to know the error function of a number, we simply use the function that returns the probability of that number is within the defined range. Similarly, for a matrix, we can determine the error function.